Let's look at a very simple example of applying the discrete Fourier series expansion in the DFT to our discrete data. So here we have some data, we have timestamps, and we have values of our signal, the t's and the x's, and we don't have very many. So this is just a very short example. In reality, you're likely going to have thousands or millions of data points that you're able to use, but this is one we can enter quickly and do a quick analysis of. So we want to, it's instructing us to conduct a harmonic analysis, including the first three harmonics of the function below. So we have these couple of data points. Really what we're trying to determine here are the first three harmonics, which is saying we want the first three terms of that discrete Fourier series. So we're going to need to find the A0 term, A123, and B123. So using three sine functions, three cosine functions, we're going to attempt to recreate this signal based on this discrete data. So I'm going to set up a couple things first in MATLAB, and then we're going to go and look at how do we actually determine the coefficients from the discrete data based on the slides from the previous subsection. All right, so the first thing I'm doing here is I'm going to just enter my raw data into MATLAB. All right, so that's when I'll just enter this. Notice the way that we were given that data, if I look at t, it does not start at 0. It starts at the first timestamp, that first value of what I'm going to be calling dt. So it's important to note here that 1, in line 89 here where I'm establishing dt, there's a constant time step between where I sampled my data. It was 0.02 seconds apart. Also importantly, the first data point we are saying happened at 0.02 seconds, not at 0 seconds. This is really important for taking the DFT of how we're measuring time, not from 0, but from dt. So when I establish my t signal, I'm starting at dt, taking a time step of dt, and for the data we were given, it ends after 0.32 seconds. Again, this is important because of how we determine capital T, that period. We took data for 0.32 seconds, again, presuming that the first time step, the first sample was taken at 0.02 seconds. Right, then we can determine that fundamental frequency W. So this is going to be a W of 19.64 about radians per second. Again, I'll point out that the W, that fundamental frequency, we can get smaller by sampling for longer. We'll see this in the PSD example that's forthcoming, but for this one, the data were sampled at that rate and there's nothing we can really do about it. All right, now I'm establishing the number of samples that we have. That's just the length of t. We can't change that. We were given this many samples. And then I'm putting in, just from the slide, the values of x here. All right, so just so we have an idea of what the data look like, I'm going to plot what we have so far. So the time, these discrete timestamps, and I'll just do it as open circles so we can see the raw data here. All right, so these were these discrete data points that we were given. Now notice in this example, it's not a repeating pattern. We're just given kind of this very small amount. Typically, we would have data that we're taking of some periodic function that we're trying to recreate. But the DFT is going to work whether it's actually periodic or it's just this single cycle. We're going to be able to at least attempt to recreate it with these sines and cosines. All right, so this is the discrete data we want to recreate here. So now going back to the definitions for the DFT of how do we find these coefficients. Now that we have this example where we have samples, we have time steps. So we can start with this A0 term. It's going to be, again, we can add up all of the samples. This is of our signal, not of our time, but add them all up, divide by the number of samples, and then multiply by 2. So once again, really this is twice the average value of our signal. So going into the MATLAB, at least my version of the code, the first thing I'm going to find is that A0 term. So this is what I'm doing. I am using the sum function, so I'm adding up all those x values, so that's the summation part, and then multiplying it by 2 over n. So let me just run that and we can find our A0 term. So for this data, our A0 term is 69.75. So this matches exactly what the formula that we have on that slide. Now we have to go into a little bit more detail. The problem was asking us to find only the first three harmonics, meaning only the A123, B123 values. So that's going to be my M here, is the number of terms I want to take. Now I'd say oftentimes it's going to be almost always much, much higher, much more terms that we want to use to try to reconstruct our signal. And here in 98, I'm going to pre-allocate my values for my A's and my B's. Again, I'm only taking 3 terms, so I'm just making sure that I have the right sizes for when I go into the for loop in the next step. And then what I'm going to be calling Y, that is going to be my reconstructed signal. So that's going to be my A0 over 2 plus that summation stuff. So that's what I'm doing in 99, is I'm going to allocate the space for Y to exist. So notice here, in this example, I'm doing Y as just this row vector. So every element in Y is a different timestamp. So it's starting at dt, and it's ending at 0.32 by the last column. So what I'm doing in 99 is, since I know it's A0 over 2 plus that summation, I put in that A0 over 2 value, and in this example, the way I'm going to find my Y is every time I go through the next loop, I'm just going to keep kind of tallying it up or summing it as I go. We're going to see in further examples, I'm going to want to keep track of my elements as I go, but in this case, I just care about keep adding the next value, the next value, the next value to my Y. Now I can find my coefficients, the A123 in this one and the B123, again using these equations. So for the little nth value of A, I want to take the summation of, again, I'm going to take each individual timestamp of my signal, multiplied by this cosine term, and then for A1, it's going to be 2 pi over t times then the value of the time. And then I'm going to add to that the second term. So what's my second signal? The time of the second signal. Add to that my third signal, and then the time at the third signal, and sum that all up. So as we're going to see, I'm doing the for loop part in the code we're about to see is going to be iterating on little n, so I can find A1, 2, and 3. And then inside the loop is where I'm going to be doing the summation part per value of little n. And then I do the same thing for the B values. So now implementing this in the code. So again, this for loop 100 to 104, this for loop is going to be making my little n value 1 and then 2, and then in this case, I'm only going up to 3. So let's see, how do I find the nth value of A? For A is 1, or A sub 1, A sub 2, A sub 3. This is where I'm doing the actual summation part. So I am taking my x values, which is the actual signal, and then multiplying it by the cosine of 2n pi times t over my period of capital T. Right, so let's just, for example, see how this works. So if n is 1, I'm doing here, these are all my x values. That was just given to me. And then here, I'm taking the cosine of 2, n is 1 for this example, pi times my time vector over t. And then I'm going to be multiplying them together. So I'm using the dot multiply here so that I am doing an element-wise multiplication. Then I'm taking the sum of that, then multiplying by 2 over n. So 101, 102 are really matching what the slide is doing. I'm just translating that into MATLAB. So then what I'm going to do is at the end of each iteration of this loop, I'm going to take the current value of y, that's my reconstructed signal, and I'm going to add this nth value of A and B that I just found. And again, back to the equation, what this line is doing is really what is up here, is I'm going to, on each iteration of this for loop, I'm going to add the nth value. So I found my AN and my BN inside that loop, so each one gets multiplied by the cosine term, and then the B by the sine term, and I'm going to keep adding this to what I'm calling capital Y as I go through my loop. So again, back to the code. So y is being built up. I'm taking my previous value and I add on a little bit. Now in the next iteration through, I'm taking the value I had, I add on the next little bit. Then the last time through, I take what I had and I add on that third little bit as I'm going through this summation. So by the end of this for loop in 104, my capital Y has my constant term and it has the 3 iterations of that summation that uses A1, B1, A2, B2, A3, B3. So let me just go through this for loop and process that. All right, so completed my for loop. So if I see what happens at the end, if I print out A, these are the A1, 2, 3 values since I have it storing it each time since I'm indexing A, and the same thing for B. So I found my first three A values, my first three B values. And in addition, the Y, which it was tallying along the way, these are now my reconstructed X signal from my original data. This is using the discrete Fourier transform, my reconstructed signal, kind of my estimate as to what the original signal was. So let's see how it does. So I'm going to plot my results. I'm going to plot my original data points versus, so that's the X, versus my reconstructed, again, using only a 3-term approximation here. So if I make this plot, I'm going to be able to see the difference between my estimate and the actual. All right, so this is what I get for that first figure. Make it a little bit larger here. So black, really the dots are the most important. That was my actual data points. And then the red dashed line is my reconstructed signal using the first 3 terms only of that discrete Fourier transform. So notice, at least by eye, okay, it doesn't look too bad. It kind of gets the general shape. It has that first bump that's pretty high, the second bump that's a little bit lower, and then it comes back down. All right, so we have fulfilled what the question asked of us. It's not very interesting at this point, but just want to show kind of a small scale version of doing this DFT so that when we get to the larger version next, we understand a little bit about the mechanics of what the code is actually doing. Because again, in actuality, we probably want to take more terms so that we have a little bit better agreement between our reconstructed signal and the original signal. Right, so the last thing I'll do here just for this example is I want to find the RMSE, the root mean squared error. Now, typically, how we use RMSE is going to be some judgment about how well our reconstructed signal is compared to the original signal, because we might have we're going to kind of see our error dropping typically as we add more and more terms to our reconstructed signal. So what we do here for the RMSE is I'm going to take my original data points, the actual measured ones, minus my reconstructed ones. So I'm just taking the difference between the two. And I'm going to then take the norm of this vector. So again, what the norm is doing is it's taking the square root of the sum of the squares of my vector. So it's going to square my first term plus the square of the second plus the square of the third and add up all of them. And then it's going to take the square root. So if I run just that norm, I'm going to get just a constant value. Right? So I get 10.88. And then what we do is we're going to divide that by the square root of how many terms were in our signal. And that is going to give us the root mean squared error. So it's going to give us, as we'll see in following examples, a kind of a basis of comparison for how good our reconstructed signal is. Because if we keep adding more and more terms, that square root term is going to start to get larger and larger. So for this one, we have this root mean squared error, and if I display it, we get 2.72. On its own, this number does not really mean much. What we're going to be looking for in subsequent examples is that how does that number decrease as we add more and more terms into our discrete Fourier transform.